Hello everyone. We are going to continue with predicate logic and quantifiers. Okay, now today we are going to discuss nested quantifiers and other topics. Okay, we're starting with nested quantifiers. Now, just like quantifiers can be loops, nested quantifiers will be nested loops. Okay, so nested quantifiers are when one quantifier is within the scope of another quantifier. It's like saying for x is equal to 1 to 10, and within for x is equal to 1 to 10, we have another for loop for y is equal to 1 to 10 or whatever other values. Okay, so everything within the scope of the quantifier can be thought of as a propositional function. So look at this example has got two quantifiers and these are nested quantifiers. So the opening quantifier is for all x. Okay, so there exists y, x plus y is equal to 0 can be considered as a single proposition. Okay, so if we look at there exists y, x plus y is equal to 0 as qx, then this statement will be for all x qx, where qx is equal to another quantifier statement, which is there exists y, px comma y, which is a predicate or a propositional logic or a logical expression. Okay, so there exists y px comma y, where px comma y is equal to x plus y is equal to 0. Okay, so these kind of statements are called there exists y, x plus y is equal to 0 comes within the scope of for all x. Okay, so these kind of statements are called nested quantifiers. We're going to look at some examples. In these examples, we are going to assume that x and y are both the domain of real numbers. Okay, now we have the nested quantifier for all x, for all y, x plus y is equal to y plus x. Okay, so if you look over here, for all real numbers x and for all real numbers y, the x plus y is equal to y plus x is actually the commutative law for addition of real numbers. Okay, so this is the nested quantifier statement for the commutative law of addition of real numbers. Now let's look at the next example. For all x, there exists y such that x plus y is equal to 0. Okay, so that means for all real numbers x, there is a real number y which satisfies the condition x plus y is equal to 0. This in effect is the additive inverse of real numbers. Okay, that is y will be minus x. Okay, then x minus x is equal to 0. Now let's look at the third example. For all x, for all y, for all z, x plus y plus z is equal to x plus y plus z. Again, all these are real numbers. So this is in effect the associative law for addition. Okay, all these are examples of nested quantifiers. Now let's look at another example. Translate into English statement. For all x, for all y, x greater than 0 and y greater than 0 implies xy is less than 0. Sorry, x greater than 0 and y less than 0. That means x is positive whereas y is negative. Okay, and is if x is positive and y is negative, then it implies that xy is less than 0. A positive number and a negative number, when it is multiplied, it will be a negative number. So it will be less than 0. This is the statement that is shown over here. Okay, and since the domain is real numbers, this is valid. Now, quantification of nested quantification as loops. Okay, earlier we saw how loops is connected to the universal quantifier and the existential quantifier. Now we are going to look at combinations. When two universal quantifiers are looped, what happens? Okay, so we have for all values of x, all values of y, px comma y will be true. So we have a loop with all x values, and within that loop we have a loop with all y values. And if the expression px comma y returns the answer true for all the x and y values, then this particular statement is true. Okay? Otherwise, the statement will be false. Okay? Next, for all x, there exists a y. Okay, so for all x values, there should be at least one y value for which px comma y is true. Okay, so inside the outer loop, there should be at least one value of the inner loop which gives the answer true. Only then the statement is true. Otherwise, the statement will be false. Okay, next is there exists x for which all y values will give px comma y true. So here what we need to do is we need to find at least one x value for which the all corresponding y values will give the expression px comma y the value true. Only then this statement is true. Otherwise it will be false. Okay. Then we have there exists x, there exists y, px comma y. So now we need to loop through all values of x within which all values of y are looped through, and for each value of, that is for one value of x, we need to find one value of y for which px comma y is true. So for each x, we loop through the values of y until we hit at least one x for which one y is giving px comma y the value true. Only then the statement will be true, otherwise that statement will be false. Okay, now what is the order of quantifiers? That is nested quantifiers. If we have through two for all statements, what is the order? Okay, if we have one for all and one there exists statement, then what is the order? Okay, if we have two there exist statements, what is the order? This is what we are going to look at. Okay, we are going to go through an example first. Let p of x y be the statement x plus y is equal to y plus x. What are the truth values of the quantification for all x for all y pxy, and for all y for all x pxy, where the domain is real numbers? We know that for all real numbers, if we look at the first one, then for all real numbers x, for all real numbers y, x plus y must be equal to y plus x. And for all y, for all x is just a similar statement. There is no actual difference between these two statements. We are saying for all real numbers, taking two, real numbers, x plus y will be equal to y plus x, the commutative law of addition. So this means the same. So what does it say about the order of quantification? Okay, if we have two or more nested universal quantifiers, then even if we change the order, if there are no other quantifiers other than universal quantifiers, okay, so there is no other quantifier other than universal quantifier in my nested quantifiers, then changing the order will not have any change in meaning. I can change all, since all the quantifiers are for all, I can change the order, there will not be any problem. But if there is one existential quantifier, then I cannot change the order. Okay, let's look at another example. Let q x comma y denote x plus y is equal to 0. Okay, and the question is, what are the truth values of the quantification? There exists y for all x such that qx, and for all x there exists y such that qx, and here also the domain is all real numbers. Okay, so let's look at the first one. There exists y for all x q x comma y. Okay, this actually is denoting that there is a real number y such that for every real number x there is an additive inverse. Okay, and this statement, there exists one y. Okay, there is, that is what the statement means, that there is one real number which is the additive inverse of all other real numbers. Is that true? That is not true. Okay, every real number has got an additive inverse, but there is no one additive inverse for all real numbers. Okay, so this statement is false. Okay, whereas the second statement, for every real number, there is an additive inverse, is true. Okay, so now we can see that if I change the order of an existential quantifier which is combined with a universal quantifier, then the answer is not going to be, they are not equivalent statements. The answer is not going to have the same truth value. Okay, so I cannot change the order when we have two different quantifiers. Okay, now the same thing is being shown over here in table format. Okay, so if you have for all x, for all y, pxy, for all y, for all x, pxy, pxy is true for every pair x comma y. Okay, if that's, the statement should be true, otherwise it will be false. If the statement is for all x there exists y pxy, then for every value of x there exists a value of y for which pxy is true. Only then that the statement is true, otherwise it will be false. Now if the statement is there exists x for all y pxy, then what we are actually saying is there is one value of x for which all values of y pxy is true. If that is the case, then the statement is true, otherwise the statement is false. Then we have there exists x, there exists y pxy, and there exists y, there exists x pxy. Here there exists a pair x comma y such that px comma y is true. If there is at least one value of x and y where pxy is true, then these statements are similar, they are true. Otherwise, the statement is false. Okay, now let's look at some examples. Again, we are looking at the order of existential statements. Okay, we have the order of quantifier, nested quantifier statements. Qx comma y comma z be the statement x plus y is equal to z. What are the truth values for all x, for all y, there exists z, qx, y, z, and there exists z for all x, for all y, q, x, y, z, where the domain of all variable consists of all real numbers. Now, if you look at the explanation over here, you see that this is exactly the same as we saying that for all values of, the first thing is saying for all values of x and y, there exists one z for which x plus y is equal to z. Okay, that statement is true because we are still dealing with real numbers. So if we have some value of x plus y, there is an z value in real numbers for which this equation is satisfied. But I cannot say that there is one z value for which all x plus y, I mean x values and y values for x plus y will be, that is the result of the addition of two real numbers. So the second statement is false. Again, we see that we cannot, when there is a combination between existential quantifier and universal quantifier, we cannot change its order. If only existential quantifiers exist, you change the order, there is no problem. If only universal quantifiers exist, then you change the order of the nesting, there is no problem. Okay, but if there is a combination and you change the order, then they are not equivalent statements. Their truth values will not be the same. Okay. Now, we are going to look at translating mathematical statements into nested quantifiers. Look at the statement. The sum of two positive integers is always positive. We're going to convert this into a logical expression. So the first thing that we need to do is rewrite this statement to reflect the quantifier and the domain. Okay, so this we can write as for every two integers, if these integers are positive, then the sum of these integers is positive. Okay, so here the domain is all integers. And then we are giving the condition that if the two integers are positive, then, and that is if two integers are positive, that implies that the addition of those two integers will also be positive. And the statement is given over here: for all x, for all y, if x is greater than 0 and y is greater than 0, this condition is saying that x and y should be positive. It implies that x plus y, addition of two positive integers, will also be positive, will be greater than 0. And the range over here, sorry, the domain over here is all integers. We are not talking about only positive integers. But the same thing could have been written as for all x, for all y, x plus y greater than 0, and the domain is only the positive integers. In that case, we don't have to specify that x is greater than 0 and y is greater than 0. Okay, so depending on what our application is, we can choose to write the statement in this format, or we can choose to write the statement in the second format, whichever is needed for our application. Another example: every real number except 0 has a multiplicative inverse. And what is multiplicative inverse? It means that there is a value y such that xy is equal to 1. We already know that the range is real numbers except 0. Okay, so in effect what we are saying is for every real number x, if x is not equal to 0, it implies that xy is equal to 1. And it can be written as for all x, x not equal to 0 implies there exists a y such that xy is equal to 1. Okay, this can also be simplified as, since y is only in the second part, the range of y is only in the second part, I can write it as a nested statement. For all x, there exists y such that x not equal to 0 implies xy is equal to 1. That's also, I mean, it will be the same statement, it's the equivalent statement. Next example, use quantifiers to express the definition of the limit of a real valued function f of x. Okay, the variable x is a real value at a point a in its domain. So in effect the statement is limit x tends to a, f of x is equal to L. Okay, so what does this statement mean? Let's look at the definition. The definition of limit x tends to a, f of x is equal to L is given as for every real number epsilon greater than 0, there exists a real number delta which is greater than 0 such that f of x minus L is less than epsilon whenever 0 is less than absolute value of x minus a less than delta. So the absolute value of x minus a must be between 0 and delta value. Okay. So for every real number epsilon which is greater than 0 means positive real number epsilon and positive real number delta, x minus a must lie between 0 and delta for fx minus L to be less than epsilon. This is actually the meaning of this definition. We have learned it in integration and differentiation, things like that. Limits we have learned. This is the definition. Now, if you have not learned limits, this is the definition. Now, to reflect this particular statement, what is the quantifier that you can use? Okay, so this definition of limit can be phrased in terms of quantifiers. Okay, so in effect, we are saying for all epsilon, for all delta, sorry, there exists delta for all x such that 0 less than absolute value of x minus a less than delta implies that this is true. Okay, f of x minus absolute value of f of x minus L is less than epsilon. Okay, but in this we have not specified that the real numbers epsilon and delta should be positive. Okay, so here the domain is all positive real numbers. Okay, where, sorry, the condition is given where the domain for the variables delta and epsilon are all positive real numbers and x contains all real numbers. Okay, now these, instead of writing the domain of delta and epsilon are all positive real numbers and x is all real numbers, both positive and negative, instead of writing it like that, we can change it like this. Okay, so it can also be expressed as for all epsilon greater than 0, for all delta greater than 0, for all x, and then the condition of limit, and the domain for epsilon, delta, and x are all real numbers. Okay, so either way, this is the representation. Please learn the definition, the statement of limit of a real valued function f of x by heart, because other questions can also be asked. If you don't remember, please learn this by heart. Okay, so limit x tends to a f of x is equal to L actually means that there exists a real number delta, a positive real number delta, and a positive real number epsilon, such that absolute value of x minus a is between 0 and delta, such that absolute value of f of x minus L is less than epsilon. Okay, please learn this by heart. Only then we will be able to do the other manipulations with quantifiers. Okay, next example, translating from a nested quantifier into English. Okay, so the question is, let the nested quantifier be for all x, c of x, or there exists c of x, c of y and f x comma y into English. And it is given to us that c of x is, x has a computer, f x comma y is, x and y are friends, and x and y are from the domain of all students in your school. Okay, so we know what c of x is. So this particular statement, it will be for every student x in your school, x has a computer, or there exists a student y who has a computer, and x and y are friends. Okay, so in other words, it means that for all the students in our school, there is, they have a, either they have a computer or they have a friend who has a computer. Okay, that's the translation. Another example, the nested quantifier statement is there exists x for all y for all z, f x comma y and f x comma z, and y is not equal to z implies not f y comma z. And it is given that f a comma b means a and b are friends, and the domain x, y, and z consists of all students in your school. So what does this statement mean? Okay, first let's leave the quantifiers and let's do the inside statement. What does it mean? this expression, only the inside statement, this expression says that fx comma y is x and y are friends, and x and z are friends, and y and z are not the same student. Okay, so y and z are not the same student. That implies that y and z are not friends. Okay, now we are going to add the quantifiers. So the statement will become, there is, the original statement will become, there is a student X for all students Y and Z, so that, such that if X and Y are friends and X and Z are friends and Y and Z are not the same student, then Y and Z are not friends. Okay, so what does that mean? It means that there is a student, none of whose friends, there is at least one student X, none of whose friends are mutually friends. Okay, so the student X has got many friends, but those people are not friends of each other. That is what the statement means. Okay, again, another example, if a person is female, now we are going to convert from sentences to logical expressions. Okay, if a person is female and is a parent, then this person is someone's mother. Okay, how do we convert this statement into a logical expression that has got predicates, quantifiers, and the domain consists of all people? Okay, first the statement, if a person is female and is a parent, then this person is someone's mother, can be expressed as, for every person X. Okay, because the domain is all people. For every person X, if the person X is female and person X is a parent, it implies that there exists a person Y such that person X is the mother of person Y. Okay, now let's take each statement. Let f of x be x is female, let p of x be x is a parent, and let m x comma y be x is the mother of y. Then the original, this statement will become, for all x, f of x and px implies there exists a y such as m x comma y. Okay, which is equivalent to, I told you, since this there exists y is only applying to the mx comma y, we can take this there exists outside. Okay, the range is only going to be in mx comma y. So uh, for all x there exists y, f of x and p of x implies mxy is the same as this statement. They are equivalent statements. Okay, another example. Everyone has exactly one best friend. As a, we have to express this as a logical expression. Okay, so let's look at the statement. Everyone has exactly one best friend, and the domain is all people. Then it can be expressed as, for all, for every person X. Person X has exactly one best friend. Okay, so the statement can be, for all X, person X has exactly one best friend. Okay, now how do we say person X has exactly one best friend? Okay, we have to say that there is a person Y who is the best friend of X, and for every person Y, if person Z is not person Y, then Z is not the best friend. So every other person is not a best friend, we have to say. So how do we represent this statement? B x comma y. Okay, let B x comma y be the statement Y is the best friend of X. Okay, and the statement that X has exactly one best friend is represented by, there exists Y such that B x comma y, that is B, Y is the best friend of X, and for all Z, Where z is not equal to y, z is not the best, it implies that z is not the best friend of x. Okay, only then we can express the statement that x has exactly one best friend. Okay, so there exists a y such that bx comma y means that y is the best friend of x, and there are no other best friends. That has to be represented using for all z, where z is not equal to y implies not bx comma z. So now clubbing the two, we get the original statement for all x, there exists y such that bx comma y and for all z not equal to y implies not bx comma z. This is the original statement. One has exactly one best friend. Okay. Another English statement, okay, to be converted into a logical expression using quantifiers. There is a woman who has taken a flight on every airline in the world. There is a woman who has taken a flight on every airline in the world. So we can see there exists a woman, there exists a flight for all airlines. So that is what we need. So if W is the representing woman, F is representing flight, and A is representing airline, then we have the statement P, W, comma F, which is W has taken flight F. Woman has taken flight F. Okay, and QFA is flight is, F is a flight on an airline A. Then this statement can be expressed as there exists W for all A, there exists F such that PWF and QF comma A. Okay, now this statement has been represented, and the domain is W and WF and A are, W is women in the world, flight is flights on an airline, and A is all airlines. Okay, now negating nested quantifiers. Before wherever negation comes in, we use the rules of De Morgan's law. So wherever you see for all, it will become there exists. Wherever you see there exists, it will become for all. And if you see other, logical expressions or operators or and or, it will become the opposite. Equal to will become not equal to, and will become or, etc. Okay, so for this particular statement, for all x, there exists y, xy is equal to 1, one by one you will negate. So the for all will become there exists will become for all, and xy equal to 1 will become xy not equal to 1. So the statement is, the negative statement will be there exists x for all y, xy not equal to 1. Okay, just apply negation one by one using the De Morgan's law for quantifiers. Similarly, they are asking us, they're giving an English statement. There does not exist a woman who has taken a flight on every airline in the world. It is the negation of the earlier statement where we said that there exists a woman who has taken a flight on every airline in the world. So the statement that we had was there exists W for all A, there exists F, PW, comma F, and QF comma A. Now when we negate this, it will become there exists will become for all will become there exists, and will become or. So the statement is for all W, there exists A for all F, not PW comma F or not QF comma A. Okay, so that is the De Morgan's successively applied to the nested quantifier. Now, this is the limit statement, and we are supposed to find the negation of the limit statement. We already know the nested quantifier statement for the limit statement. It was given as for all epsilon greater than 0, there exists delta greater than 0 for all x such that 0 less than absolute value of x minus a less than delta implies absolute value of fx minus L less than epsilon. Okay, now if you want to do the negation of this statement as earlier, for all will become there exists. So it will become there exists epsilon greater than 0 for all delta greater than 0, there exists x. But now this is a logical expression. So the negation of this expression. To do the negation of this expression, first we will change P implies Q to not P or Q. Okay, so this inside, please look at my arrow. This inside statement, the left hand side is P implies the right hand side Q. So the left hand side P implies Q is equivalent to not P or Q. Okay, so this will become not 0 less than absolute value of x minus a less than delta. Okay, and this Q is, it will become or absolute value of fx minus L less than epsilon. And then you negate. When you negate, negation of negation P is P itself. So this statement will be 0 less than absolute value of x minus a less than delta. The or will become and then you have the right hand side Q. So absolute value of fx minus L, not Q. So absolute value of fx minus L, here it is less than epsilon, here it should be greater than or equal to epsilon to designate not Q. Okay, negation of not P or Q is equal to P and not Q. Okay, so that is what is given over here, the negation of this expression. Okay, now I'm just going to introduce the rules of inference. We will look at examples in detail in the next class. Okay, now what is rules of inference? We learned all these things to show that we can use these rules of propositional logic and logical expressions, quantifiers, etc., to infer new things and to explain the validity of arguments. In effect, what we are doing is we can use these rules to create proofs. Okay, so rules of inference are the fundamental tools which are used to establish truth in mathematics. Okay, so we deduce statements from already existing ones and we create or construct valid arguments. Okay, now these rules of inferences not only help us to create valid arguments, it also helps us to identify logical fallacies or invalid arguments. Okay, so they can be applied to propositional logic, to quantified statements, to others, because natural language statements can be converted into propositional logic and quantified statements. This rule can be applied to check whether arguments are valid. Okay, they are combined to create complex arguments. So we are going to look at the basic rules of inference and then we will look at examples where combinations are used to construct complex arguments. Now, what is a valid argument in propositional logic? Okay, we are going to look at an example. Determine whether the conclusion you can log on to the network is true when the premises is given as if you have a current password, then you can log on to the network, and another premise is you have a current password are both true. Okay, so I have two statements. Let P be you have a current password, and let Q be you can log on to the network. Then the first premise, if you have a current password, you can log on to the network is P implies Q. Okay, and the second premise, you have a current password, is P. Okay, if both P implies Q and P are true, then this kind of argument is of the a particular form. Okay, we're going to look at different forms of arguments a little later. This particular argument is a valid form. Okay, since it is a valid form, which is also called a tautology, that is, if P implies Q is true and P is true, automatically it implies that Q is true. It is a tautology. So this particular argument is valid since all its premises are true. That is, P implies Q is true and P is true. Since both are true, this is of valid form and Q will also be true. That is, Q is a valid conclusion. Okay. Now let's look at an example where the form is the form which we saw earlier, but both premises are not true. Okay, so suppose that P represents you have access to the network and Q represents you can change your grade, and that P is true, but P implies Q is false. Okay, you have access to the network is true, but because you have access to the network, you can change your grade is not true. It's false. Then if we look at this particular same form, okay, the format is the same, but the first premise is false and the second premise is true. Okay, then Q cannot be true. Okay, only if both P implies Q and P are true, Q will be true. It is a valid argument form. Okay, if one is false and the other is true, then Q doesn't automatically follow. It is not a valid argument form. So the conclusion, we cannot conclude in this case that the conclusion is true. Okay, now let's look at terms. Okay, an argument is a propositional logic in a sequence of propositions. All but the final proposition in the argument are called premises, and the final proposition is called conclusion. We saw that earlier. Okay, the argument is valid if the truth of all its premises implies that the conclusion is true. So the argument will be valid only if the truth of all the premises implies that the conclusion is true. Okay, now what is an argument form? It is a sequence of compound propositions involving propositional variables. Any sequence is an argument form. But if the argument form should be valid, then no matter which proposition is substituted for the propositional variables in its premises, the conclusion is true if all the premises are true. Okay, so for the argument to be valid, say that there are n premises, then adding all those premises, it implies Q if it is a tautology. All 1 values alone will give you Q equal to 1. Okay, so in other words, to show that an argument in a propositional logic is valid, we need to show that its argument form is valid, that it is a tautology. Okay, now let's look at the rules of inferences for propositional logic. One form we have already learned. I have not shown you the the names of these rules of inferences. We are going to look at the names right now. Okay, as usual, truth table could be used to show that a particular argument form is valid. But problem is, as the number of propositional variables increases, truth table becomes difficult. Okay, so rules of inferences are simple argument forms used as building blocks to construct more valid argument forms. So we use these simple rules of inferences to show that other argument forms are valid. Okay, of which the first one we have already seen, P implies Q and P implies Q only if both P implies Q and P are true. This is called modus ponens or the law of detachment. If both the premises are true, then the conclusion is true. Okay. Now, suppose that the conditional statement, if it snows today, then we will go skiing, and its hypothesis, it is snowing today, are true. So now this is of the form P implies Q and P. If both these are true, then Q is true. We will go skiing is true. Okay, this is an example of modus ponens. Now let's look at this example. Okay, here it is given. Determine whether the argument given here is valid and determine whether its conclusion must be true. Because of the validity of the argument, if square root of 2 is greater than 3 by 2, it implies square root of 2 the whole square is greater than 3 by 2 the whole square. If this is true, then this is true. But we know that square root of 2 is greater than 3 by 2. Is that true actually? Is this statement a true statement? Square root of 2 is 1.414, etc. 3 by 2 is 1.5. Is 1.4 greater than 1.5? The statement itself is false. So P implies Q in this particular case is false. Okay. So, since P implies Q is, P is false in the statement P implies Q, one of the statements is this P implies Q here is true, but P is false. So, this is not of the form modus ponens, and that is why we cannot conclude that Q is true. Have you understood? The statement is of the form P implies Q and P. P implies Q is true, but P is not true. So we cannot imply that Q is true. Okay, now let's look at the other rules of reference. We already saw modus ponens. Now we are going to look at modus tollens. What is modus tollens? If not Q and P implies Q is true, then not P is true. Okay, not Q and P implies Q is true, then not P. That is modus tollens. Now, if P implies Q is true and Q implies R is true, then P implies R is true. This is hypothetical syllogism. You need to learn all this by heart. Okay. Now, if P, you can prove all this by using the truth table. Okay. Now, disjunctive syllogism. What is disjunctive syllogism? If P or Q is true and not P is true, then Q is true. This is disjunctive syllogism. Then we have addition. P is true, then P or Q will be true. If P is true means P value is 1. So P or Q will be true. That is simple addition. Then simplification, P and Q is true. If P and Q has to be true, then P value should be 1 and Q value should be 1. Right? So that implies P is true because P is 1. Okay, so this is simplification. Okay, now P is true and Q is true, then P and Q is true. This is simple conjunction, and that is just, comes from the implication itself. Okay, now we are going to look at resolution. P or Q is true and not P or R is true. Then in that case, this P and not P is completely disappears. And we've seen this earlier. So please go check in the earlier lessons. This implies Q or R. This is called resolution. Okay, so we have 8 different rules of inferences. In the next class, we will look at examples using these rules of inferences. So for now, I'm going to stop. Bye-bye.